How does a pile of raw data actually become an intelligent AI? It's not magic. It's a series of high-stakes decisions made during the building process. Today, we're becoming AI architects, looking under the hood at how AI is built, tested, and optimized for our world. Building an AI model is an iterative journey. Each pass through the training data is called an epoch. In practice, models are trained over many epochs as the algorithm repeatedly sees the same information to fine-tune its parameters until they converge on accurate predictions. But first, we must address the quality of our foundation. Data imbalance, where one category is overrepresented, can lead to biased models. If a face recognition system is trained on 90% of one ethnicity, it will naturally fail to recognize others accurately. To fix this, we use techniques like oversampling the minority group or generating synthetic data to ensure the AI's worldview is balanced and fair for everyone. A balanced foundation is the first step towards secure AI. Then there's hyperparameter tuning. These are the settings developers choose, like learning rate or batch size, that determine how fast and how well a model learns. Finding the right balance is an art form that directly impacts security and efficiency. Developers often use grid search to exhaustively test every combination, or random search for a faster, more efficient way to find the best settings. It's the difference between checking every single door and finding the most promising paths first. But there's a catch. More epochs don't always mean a better model. If you train for too long, the AI stops learning general patterns and starts memorizing the training data specifically. This is a critical security problem called overfitting. An overfit model performs perfectly on the data it has seen, but fails in the real world. This matters for security because overfitting is one mechanism by which a model can memorize and later reproduce sensitive details from its training set when prompted. To catch overfitting early, we use a quality gate called the validation set. A portion of the training data is held back and never used for training. Instead, the model is tested on this unseen data at regular intervals to verify its real-world behavior. If training accuracy keeps climbing, but validation accuracy plateaus or drops, that's overfitting in real time. A model that skips thorough validation is one whose behavior is unknown, and in cybersecurity, unknown behavior is a massive security risk. Once a model is trained, it often goes through compression before deployment. This is crucial for running AI efficiently on limited hardware, but it's often handled by third-party teams, which introduces an inheritance problem for security. Pruning removes parameters that contribute little to predictions, shrinking model size. Quantization reduces the numerical precision of weights, like cutting memory requirements. Both are efficiency gains, but they change how the model functions. There are two paths here. Post-training quantization is fast and simple, but quantization-aware training actually teaches the model to handle its own limitations during the training process, preserving much more of its original safety logic. Research has shown that quantization can silently degrade built-in safety mechanisms. Defenses that worked on the full precision version may fail to detect backdoors or threats in the quantized version. Organization inheriting these models may not even know what changed. Finally, we have federated learning. This was designed for privacy. Instead of sharing sensitive data, like a hospital's patient records, the model travels to the data. Participants train locally and only send weight updates back to a central server. At the center, an aggregation process like FedAge takes these individual updates and averages them to improve the global model. It's a democratic way of learning that never exposes your raw, personal files to the central server. But federated learning is a case study in security trade-offs. While data privacy is improved, the integrity of the training process becomes much harder to verify. It solves one trust problem by distributing control, but it creates a brand new one. In a federated setup, malicious participants can submit poisoned local updates, subtly manipulated gradients designed to skew the global model's behavior. Detecting this at the aggregation stage is incredibly difficult, making the integrity of the AI vulnerable. Many systems use transfer learning, taking a pre-trained giant like GPT-4 and fine-tuning it for a specific task. While powerful, this means you are building on a foundation you didn't create. If that giant has a hidden flaw, your specific model will inherit it. In transfer learning, we often keep the foundation layers frozen, meaning we don't change the basic knowledge, and only fine-tune the top layers for our needs. It's standing on the shoulders of giants, but you must know who that giant is. For organizations deploying AI, understanding the data supply chain is just the beginning. We must also audit the building process itself. From epic limits to the ML bomb, every decision matters for our long-term security. Designing secure AI isn't just about the code. It's about the trade-offs we choose to accept. By staying knowledgeable about training, validation, and optimization, you're ready to build a digital future we can actually trust. Thanks for joining me for this masterclass on model building. Subscribe for more guides on the technologies shaping our world. Stay curious, stay alert, and stay secure.